Get going. Welcome back to Codex. Today's speaker is Julia Lindberg from Georgia Tech. Professor Lindberg is an expert in applied algebra and convex geometry. Today she'll tell us about Gaussian Voronoi diagrams. Take it away, Julia.
Great. Yeah, thanks for the invitation. So I'm excited to talk about this. So this is some work that's not quite on the archive yet, but should be soon. And this is joint work with Joe Kileel at UT Austin. So let's begin with a motivating example. Suppose you have you in some kind of clinical setup and you have a patient come to you and you do like an X-ray and you see that they have a tumor and you can measure it and say that it is a perimeter of 14 centimeters. Now, the next natural question is, well, is this malignant or benign? Now, in order to kind of answer a question like this, you could do further testing, or you could try to get an estimate or kind of make a decent guess. And to do that, you would need some kind of data. And so suppose you kind of look up, data of this sort, and you come across this breast cancer of Wisconsin diagnostic data set. And then, when you kind of pull up and analyze this data, you see the following histogram. So on the x-axis, that's going to be the perimeter in centimeters of tumors. And then this is going to be a histogram of the frequency normalized so that it's a probability distribution of this tumor of a certain size being malignant or benign. Okay, so you've got this picture, you've got your one data point of that says 14 centimeters. And if you go on this histogram, you could look and say, well, okay, at 14 centimeters, this is, I guess, the histogram bar of benign is a little bit above malignant. So, maybe you'd guess, okay, this is benign. But, you can't really say that with any kind of confidence or any sort of certainty. Right. And so, the idea here is we want to make this a little bit more formal. We want to be able to make a guess and then kind of give some sort of confidence to this guess. Okay, so we're looking at this data, and then, maybe we squint a little bit more and we say, well, I guess each class sort of looks a little bit Gaussian, right? Like maybe this blue one is there's some noise, it's kind of multimodal, but again, if you kind of take enough steps back and squint enough, you could say, okay, each of these kind of subpopulations is roughly bell-shaped. Okay, and so then what you can do is you could fit a Gaussian to each of these curves. And if you do that, you get you get the following means and variances, right? And then now with this, we can again look at these Gaussians and estimate that actually, okay, a tumor here is more likely to be benign, and moreover, we can say with some sort of confidence that likelihood, right? And so in this case, we'd say with probability roughly 0.65. Okay, and so this is a pretty standard kind of classification procedure. And what this is an example of is something known as Gaussian discriminant analysis. Okay, and so Gaussian discriminant analysis is a supervised learning algorithm for classification. And so what you do is you assume you are given labeled data. So in general, I can do D-class classification. So in our last example, we did binary classification, so D was equal to 2. But in general, we could have D classes that we're trying to classify here. And we assume each is distributed as a mean, as a Gaussian with mean mu I and variance, covariance matrix sigma I. Okay, and so if you're given your labeled data, you can then fit an n-dimensional Gaussian to this data. And you assume that your data came from a distribution with this exponential density. Then the way Gaussian discriminant analysis works is you are given some new data point and you classify it as class I if the density at the ith Gaussian is greater than or equal to all the other ones at that same point. Okay, so again, kind of a pretty straightforward procedure for classification here. So although this is, kind of a relatively simple, data science algorithm, there's still kind of quite a few interesting things to say about it. And so what we're going to be interested in is namely the set of points that get classified as a certain Gaussian. Okay, and so this is kind of our main definition and our main object of study. And so I assume I'm given some set of some finite set of Gaussians. And so this is my set X, and throughout this talk, we'll assume we're given D Gaussians. Then the points that would be classified as class I is going to be called the Voronoi cell of this ith Gaussian component. By taking logs and then kind of doing some basic algebra, we can get this nice semi-algebraic description of the ith Gaussian Voronoi cell. Okay. The Voronoi diagram of X is then going to be the union of all of these Voronoi cells. Okay, so here's just a little example. If, say, I have these two Gaussians. So again, the kind of setup is that I'm given labeled data, and then I fit a Gaussian to each of my classes. And suppose after I do that, these are the Gaussians that I'm given. So they both have mean at the origin, and then one has identity covariance. The other has this diagonal covariance with a 4 and a 1/3 on the diagonal entries. So then the Gaussian Voronoi diagram is this two-dimensional picture here, and everything in blue would get classified as the second Gaussian, and everything in purple would get classified as the first. Okay, so one kind of observation immediately from this semi-algebraic description is that each Gaussian Voronoi cell is defined by d-1 quadratic inequalities. And so that's why maybe you've seen this in the literature as quadratic discriminant analysis, or QDA, it's often called. Okay, so these Gaussian Voronoi cells and these diagrams are going to be kind of a main object of concern. And so before we get kind of too far into things, I want to look at a couple examples. And so the next example that we could consider is what happens if I consider this special case where all the covariance matrices are just the identity matrix. Right? Now, in this case, we can do kind of just substitute in the identity matrix to our definition. And what we see is that the Gaussian Voronoi cell of the ith Gaussian is actually just the standard Voronoi cell, but with respect to the finite point set given by the means. And so in particular, in this setup, Gaussian Voronoi cells are just standard Voronoi cells. And so you can really think of these as generalizing this kind of very classical and well-studied geometric object. Just kind of one additional note in this case is I can slightly relax this identity assumption and just say, what happens if all the covariance matrices are equal? Well, then in this case, each Gaussian Voronoi cell is just a linear transformation of the standard Voronoi cell. And so in particular, it'll be each Gaussian Voronoi cell will be described by up to d-1 linear inequalities. And so that's why this special case where all the covariance matrices are the same is sometimes referred to as linear discriminant analysis. Okay, very good. So let's keep going. Let's look at another example. Okay, and so this linear case, I guess maybe the takeaway is that it's we kind of know a lot about it. So we're mostly interested in what kind of behavior can happen when my covariance matrices aren't the same. So here are 4 pictures, right? And so in each of these cases, all of my means are the same, and then I'm just varying the covariance matrices here. And so kind of the observation here is just like a lot of things can happen, even in just 2 dimensions with just 4 Gaussians. So, you can see here that I start and this green Gaussian Voronoi cell is bounded. And then when I change my covariance matrices, now all of a sudden it's unbounded, right? And then in this case, this purple cell has 2 connected components, and then when I vary my covariance matrices again, it now just has 1. Right, and so you can just kind of already see how much more expressive these Voronoi cells can be once I allow non-identical covariance matrices. And so what we're really interested in is kind of trying to get a little bit of a handle on the types of behavior that we can see. And kind of one key difference that will come up a little bit later that I want to highlight is I want to zoom in on this first picture and this last picture. And so if I do, this is what we get. And what these yellow stars are, these represent the mean. So these 4 points here. And what you can see in the standard case is that each mean lies in its own Voronoi cell. And this is kind of pretty straightforward to see just by the definition. Now, in contrast, on the left here, we see that here three of the means lie in one of the cells and another mean lies in another. Okay, so just kind of off the bat, this is already a different sort of behavior that we're seeing. But more importantly, in the standard Voronoi cell case, you can use the fact that each mean lies in its own Voronoi cell to show that each Voronoi cell will be non-empty. And for this general case, we don't have that, right? And so kind of just off the bat, we can already see like there's going to be some slight complications when generalizing. Okay. And so the goal really of this work is to understand the geometry and the combinatorics of these Gaussian Voronoi cells / diagrams as a whole. And so the outline really is we're going to start with some of our geometric results and then turn to some of the combinatorial results. But before we do that, I want to maybe motivate this a little bit more. So this is, I think the title of the seminar said the seminar on theory and applications. And okay, so I gave you like the data science application, but you might ask, kind of why, even if I care about this specific problem of Gaussian discriminant analysis, why is studying Gaussian Voronoi cells sort of the right approach to take? And so one note is that these Gaussian Voronoi diagrams are going to give us all possible clusterings, something known as Gaussian mixture models are capable of producing. So these Gaussian mixture models are just convex combinations of Gaussian densities, and they're used all over data science because they're essentially universal approximators of smooth density. So they kind of come up over and over again in many different contexts. And what we see here is that these standard Voronoi cells, as we saw in the case of like linear discriminant analysis, these can only give convex clusterings, right? And in real life, our data is not always convex, right? And so what a standard procedure to do is to use something like, say, kernel methods and take my non-convex data and embed it into some high dimensional space where then it is convex. So these clusterings form convex clusterings. And then do some kind of convex optimization procedure in this higher dimensional space. And while these kernel methods are kind of very powerful and they have seen a lot of success, the issue here is I'm now kind of losing a lot of my interpretability of my data once I embed it into this higher dimensional space. And so our philosophy of our approach is, well, okay, what if I just keep it in my kind of ambient dimension space, like the dimension my data actually belongs in, and just try to get a handle on how on the non-convexity and kind of how things can behave in this ambient dimensional space. Another note is that because we have this nice semi-algebraic description, we can use results and kind of algorithms from real algebraic geometry to say, find a sample point on each connected component of a Gaussian Voronoi cell. Right, and so there's some kind of off-the-shelf algorithms we just get access to right away. In addition, the geometry of these Gaussian Voronoi diagrams are going to give us a priori information on pitfalls with certain models. And so this is something that I will talk about in a lot more detail once we kind of move on to some of our results. And so with this in mind, a question, we can kind of think of a motivating question as sort of, okay, so what clusterings are these Gaussian mixture models, or these kind of collections of Gaussians capable of producing? Okay. And so with that, let's get started. So as I said, we're going to start with the geometry and then move into some of the combinatorics. Unless if there's any questions, I can also pause if there's a question. Okay. Okay. So the first thing that we're going to define is something called the decision boundary. So this is essentially the set of points who are equally and maximally likely to belong to a given Gaussian. Okay? And we can kind of explicitly write this out as, essentially what you need is these likelihoods to be equal for two different Gaussians, and then to also be maximal among the others. So for a given Gaussian Voronoi cell, I can then see that the Zariski closure of the boundary of this Gaussian Voronoi cell is going to be contained in the hypersurface that I get if I just multiply kind of all of the pairwise all of the pairwise polynomials of setting, the ith likelihood equation equal to the jth one. Okay, and so why do I want to do this? Well, now I at least kind of am setting my problem up so that I can get an upper bound essentially for free. So there's this celebrated Milnor-Tom result that says the number of connected components of the complement of a degree k hypersurface in R to the n is k to the n plus 1. And so using the fact that my number of connected components is at most the complement of the number of components of this hypersurface, then I can apply this result. And I can see that the number of connected components of a given Gaussian Voronoi cell is at most 2d minus 1 to the n plus 1. Then if I add all of those up, the number of connected components in my Gaussian Voronoi diagram is at most d times 2d minus 2 to the n plus 1. Okay, so just kind of an example of if I sort of set things up properly, I can, use existing results and get an upper bound essentially for free. And so, okay, that's nice, but as you might imagine, we don't think that these bounds are tight. Okay, and so in particular, we can consider the one-dimensional case. And if we take a collection of Gaussians and we put a partial ordering on them by the variances, so we make the variances increasing, then we can show that the number of connected components of a given Gaussian Voronoi cell is at most I, and the number of connected components of the whole diagram is at most 2d minus 1. Okay, and so I guess just maybe two notes here. So one is that these bounds are actually tight in this case, and you can plug in n equals 1 here and see that then this means that neither of these bounds are tight, even in this kind of smallest example. Moreover, there is kind of more going on, I'll say, than just sort of accurately bounding the number of components of the given cell and then adding everything up. So, if I added up the sum from, I equals 1 to d of I, of course, I get d choose 2, right? So something quadratic in d, but actually the number of connected components is at most something linear in d. And so there's kind of two pieces here. Is this Milnor-Tom result isn't tight even just for the individual cell, but then sort of adding up the maximum number of components of the individual cells still won't give you something tight for the whole diagram. And so there's some kind of dependencies among each of these cells that's kind of really restricting how many connected components we can have. Okay, and so as I mentioned, these bounds are tight, and let me just kind of give you a little toy example here so you can see at least where the number of connected components of the diagram being 2d minus 1 is tight. And so if you consider the example where all of these Gaussians have 0 mean and then the variances are strictly increasing, if you plot out these densities, what you'll see is you get this kind of nesting behavior. And so this is one instance that attains this 2d minus 1 maximum number of connected components. Okay, and so this is maybe like, how do you say, like a first natural question. I have some semi-algebraic sets. It's like, what's the maximum number of connected components? And I argue that this is still useful from, like an application perspective, just to know how many disjoint subsets could be clustered into the same class. But from an algorithmic perspective, I claim actually the lower bound is probably going to be more important to us. Right? And so this Milnor-Tom gives us an upper bound, but the question is okay, can we get a decent lower bound? And so as I kind of already alluded to earlier, one difference between Gaussian Voronoi cells and regular Voronoi cells is that these Gaussian Voronoi cells can be empty. And so even just in one dimension, here's an example where I have 4 Gaussians, and you can see this third one, which corresponds to this green density. This Gaussian Voronoi cell is actually empty. And I'll just note it has the same variance as these first two, so it's not like if I get big enough, it'll dominate close to infinity. It's just empty. Okay. And so, the question is like, well, okay, here I needed I needed four Gaussians before I could get an empty one. And so kind of in general, what can happen? And we can show that for any dimension, there exists a collection of d Gaussians such that this Gaussian Voronoi diagram only has three connected components. Um, Moreover, we can show that this is actually tight in the sense that if you have three or fewer Gaussians, then each Gaussian Voronoi cell will be non-empty. Okay, and so maybe this is like a little bit surprising that this three is just a constant that actually doesn't depend on D or the ambient dimension. And so one kind of pretty negative implication of all of this is that it doesn't matter what dimension your data lies in. For any collection of D Gaussians, D minus three of them can actually have empty Gaussian Voronoi cells. And so what that means, if we consider our first kind of motivating example, is that in this Gaussian discriminant analysis application, it's possible that this classifier will only classify new points as three classes. And that's even in the case where you say have perfect data, as much of it as you want, kind of no noise, nothing like that. Even if you kind of ground truth estimates of each of your Gaussian classes are completely accurate and there's no noise, it is still possible that this classifier will perform essentially arbitrarily poorly. And okay, that, for that application in and of itself is sort of maybe not so great. But moreover, this Gaussian discriminant analysis is actually used as a sub-procedure in some other algorithms. And so there's this pretty popular algorithm called the expectation maximization algorithm. And there's a version of it called this hard EM. And so what this algorithm does is it takes unlabeled data and it clusters the data into classes and then simultaneously fits a Gaussian to each class. And so in contrast to kind of our original application where we assume we're given labeled data and then we fit a Gaussian and then classify, in this case, we'd be given unlabeled data. So we need to kind of cluster the data into classes and then also find the Gaussians. And so the way this algorithm works is you essentially initialize, hopefully somewhat intelligently, but then you perform Gaussian discriminant analysis to assign each data point to a given class. And then you update the means and covariance matrices to be the sample mean and covariance of all the points classified as class I. And then you just iterate until some sort of convergence criterion is met. And so because this GDA is a sub-procedure of this larger algorithm, we see that this algorithm can also perform kind of arbitrarily poorly. I just want to note that maybe if you haven't seen this algorithm under this name before, you might have seen the special case where all of these covariance matrices are the identity. And in this case, this algorithm, this hard EM, is just the k-means clustering algorithm, which is a pretty kind of popular and well-studied clustering algorithm. Okay. And so maybe some sort of negative results, but at the very least, understanding a little bit more about the geometry of these Gaussian Voronoi diagrams, it helps us pretty easily understand how some of these algorithms can have certain pitfalls. And so one thing I want to show you is just an example, say, of a case where this can happen and maybe some room for some future work. And so I'm taking this example that we had before, where this, I guess I switched the colors, my apologies. But now this red Gaussian is empty. And what I'm doing is I'm considering a sample of 100,000 samples and 1,000,000 samples. So I'm trying to consider a case where I have, a ton of samples, so kind of approximating sort of population type data. And what I'm doing is I'm running this hard EM algorithm, and I am fixing the variances. So I'm there's issues where these variances can go to zero. And so what I'm kind of assuming I know even more, and I'm fixing the variances to be what the ground truth is. And then all I'm trying to do is estimate the weight, so the percent that the percent of data that comes from each class, and then the mean of each class, running this hard EM algorithm. And moreover, I am initializing this at the ground truth. So I'm kind of trying to set this thing up to do as well as possible. And because, this maybe isn't so surprising that because we have an empty Gaussian Voronoi cell, this algorithm just can't converge to the ground truth. But maybe what's a little bit more interesting to me is we seem to see two types of convergence behavior here. And so you can see here, so I guess this blue star is under the yellow star because they have the same weight and mean. But what you can see is it sort of looks like this red component either converges, to this mean and weight or this one, and kind of similarly with some of these other ones. Moreover, the yellow component actually just converges to having weight 0 in each of these cases. And so, we know from this emptiness result that there's no way this algorithm can actually converge to this ground truth, no matter how well we set it up. But sort of what can it converge to in some of these cases is pretty open. And it seems to be like there's some kind of interesting behavior that's happening. And in particular, it's not necessarily converging to one thing. There seems to be kind of two types of convergence behavior. Okay, and so let's see, doing quite well on time. And so with that's sort of all I want to say about the geometry of these Voronoi diagrams. And so again, I can take any questions now. Otherwise, I can kind of move on to the final piece. Okay, so let's kind of finish up with some of the results that I think are a little bit more how do you say, like a little bit fun. They're maybe not as useful from an application perspective, but I think they're still kind of interesting. Okay, and so in particular, I want to talk about the combinatorics of these Voronoi diagrams. Okay, and so we're going to restrict ourselves to this one-dimensional case again. And in this case, you can see a definition kind of just simplifies to these univariate quadratic polynomial inequalities. And so here's a little example of, d equals 2 again. So I've got two Gaussians, and this picture left is the log of the densities, and this picture on the right is the actual densities. And then what you can see is these Gaussian Voronoi diagrams then weakly partition the real line, right? And so everything in orange, again, would get classified as the second Gaussian, and everything in blue would get classified as the first. And so the kind of key observation here is that in one dimension, these Voronoi diagrams live on the real line, which is a well-ordered set. And so I can associate to each of these diagrams a sequence that just tells me what order these cells appear in. Okay. And so this is a definition of a Gaussian D sequence. And so what it is it's just a sequence that if I start at -infinity, it just records the order in which I see each of these Gaussian Voronoi cells. And so in particular for this little example, what we see is if I start at -infinity over here, I start at the second Gaussian, so my first number would be 2, and then I keep walking up until I hit this blue cell, and then I switch to 1, and then I switch to the orange, so I switch back to 2 again. So kind of if I walk from -infinity to +infinity, the order in which I see these Gaussian Voronoi cells is 2, 1, 2. And so I should also point out here that our definition now, we're going to assume that we're weakly, these variances are weakly increasing. Okay, so we're ordering them now. Okay, and so in some sense, this is maybe a natural thing to do, but one thing that's nice about it is it now allows us to associate a combinatorial type to each of our Gaussian Voronoi diagrams, right? And okay, so one more example is if I have a case where all of my variances are just 1 and then the means are weakly increasing, this will have Gaussian D sequence 1, 2, 3 all the way up to D. Okay, and so again, what this allows us to do is sort of kind of organize all of the different types of clustering behavior that we see into these different combinatorial types based on these Gaussian sequences. Okay. And so, the natural question then is, okay, which sequences of D integers can then be Gaussian D sequences? And so we have an answer, and it looks really messy, but maybe let me just kind of tell you what this messy notation is saying. So I'm going to consider some sets of some sequence, and it has n integers in it, so capital N, and then each of these I sub j's is some integer between 1 and d. Okay, so this is a Gaussian D sequence if and only if, well, any two subsequent integers are not the same. Okay, so this should make sense from a Gaussian Voronoi cell perspective, because if I had two integers that were the same, that would correspond to going from one cell to the same one right next to it. So we would just count that as one cell. Okay, so that one's kind of a little bit just a kind of technicality. But the second one is actually kind of the real constraints. And so what this is kind of saying in notation is that if I have some integer L that appears twice in my sequence, then any integer that appears between the two occurrences of L must be less than or equal to it. So as an example, 3232 cannot appear as a part of a larger Gaussian sequence because the number 2 appears twice and 3 appears between 2, but 3 is strictly greater than 2. But 3212 could appear twice because even though, again, 2 appears twice, 1 appears in between it and 1 is less than 2. So we're all good. Okay. And so this kind of gives us a classification, if you will, of the different types of sequences that we can get. But then, the next question is, well, okay, so how many of these are there? And so in particular, we know from our results on the number of connected components that if S is a Gaussian D sequence, then the size of it must be less than or equal to 2D minus 1, right? Because each number in our sequence corresponds to one connected component. And we showed that there's at most 2D minus 1 connected components for a Gaussian Voronoi diagram in one dimension. And so based on that nesting example, we can generalize that and see that this sequence that goes D minus 1, D minus 2, all the way up to 1, and then back down to D, this is a Gaussian D sequence that achieves this maximal size. But we could ask, okay, is this the only one, right? Or kind of like how many of these sequences can achieve this maximal size? Another way to say that is how many different types of Gaussian Voronoi diagrams do we have that have this maximum number of connected components? Okay, well, yes, so how many are there where we achieve this maximum size? So I could use this theorem here that I stated here, and I could look at when D equals 3, and I could kind of manually sort of work out all the constraints and see that these are the only 3 Gaussian 3 sequences of maximal size, which would be 5 in the case when D equals 3. Okay, and so, the idea though is that I want to go kind of higher, right? So even when D equals 4, kind of going through that theorem, it starts to get a little bit cumbersome. And so to give a nice answer to this question, we just need one more definition, and it's that of a Stirling permutation. So a Stirling permutation of order D is a permutation of the multiset 1, 1, 2, 2, all the way up to DD, such that for every I in this permutation, the values between the two copies of I are larger than I. So for example, there are 3 Stirling permutations of order 2. So these are the only permutations of the set 1, 1, 2, 2 that satisfy this constraint, that between the two copies of I, anything in between it are larger than I. Okay, and so there is there's a nice result that says that these Stirling permutations are actually in bijection with plain recursive trees on D vertices. And so here is a plain recursive tree on D vertices. So what this is it's a tree, so you start with the root at 0, and then you can append a leaf to it. And as you follow the path down from the root to any leaf, each vertex needs to be strictly increasing. So a plane recursive tree on D vertices is going to actually have, well, D plus one vertices if you count the root. But then each vertex is given a label, 1 through D. And again, as you walk from the root down to any leaf, each path needs to be increasing. So here I go from 0 to 1 to 2. Here I go from 0 to 1 or 0 to 2. Here 0 to 2 or 0 to 1. So these are the only plane recursive trees on two vertices. And okay, yeah, so they're going to be in permutation, sorry, in bijection with these Stirling permutations of order 2. Okay. And maybe I could just tell you an easy way to see this bijection is that if I give each edge, so when I add an edge, if I give that edge the same label as the vertex, so in this case, this first edge would have label 1, the second would have label 2, and kind of so on here. And then I consider a Euler walk, so of this rooted tree, where I kind of start at the left and then I kind of start with each leaf. I kind of walk from my root down to each leaf left to right. So in this case, I would go on the vertices 0, 1, 2, 1, 0. In this case, I would go 0, 1, 0, 2, 0. In this case, 0, 2, 0, 1, 0. And if I record the edges on that walk, so in this case, I would walk on edge 1, then I'd walk on edge 2, then I'd walk on edge 2, then I'd walk on edge 1. You can see is that gives me exactly this first Stirling permutation. And similarly here, I would go 1, 1, 2, 2 to get the second one. And then in this third case, I would go 2, 2, 1, 1. And so these are just two combinatorial objects and maybe not so hard if you kind of set things up properly to see how there's a bijection between the two of them. Okay.
So in this bijection, then the specific geometric embedding of the graph is really important because you needed the way to distinguish between left and right, i.e. is it 1, 1, 2, 2 or 2, 2, 1, 1?
That's right. And so for this specific embedding, you kind of assume you have this left to right orientation on you kind of read the walk on you from root to leaf going from the leftmost one to the rightmost one. Exactly. Okay. Good. Okay, so this is some kind of studied combinatorial object. And maybe the fun thing is that we can actually show there's an additional bijection, right? And so in particular, there's a bijection between Gaussian D sequences of size 2D minus 1 and Stirling permutations of order D minus 1. And then therefore also rooted recursive binary trees on D vertices. And so in particular, because these are well-studied combinatorial objects, we can actually count the number of such Gaussian D sequences, and the number of those of maximal size is 2D minus 3 double factorial, where this double factorial just multiplies only the odd integers all the way down. Okay. And so how can we see this? Well, we can prove a bijection, a really analogous bijection using these recursive trees. So again, up top here, I've got my my Stirling permutations of order 2. And then below them, I've got the corresponding rooted recursive tree on 2 vertices. Okay, and so now I can show you then, well, I've got these are my 3 Gaussian D sequences so my 3 Gaussian 3 sequences of size 5. And how do I get this? Here's an idea of the bijection, let me say. As I start with this recursive tree corresponding to my Stirling permutation, and then what I'm going to do is I'm going to just reverse order the vertices. So instead of the vertex, the root will now be labeled as D, and then 1 will be D minus 1, 2 will be D minus 2, and all the way down. So you can see I kind of take the same tree and then just relabel the vertices. Okay, and now what I'm going to do is I'm going to do that same exact procedure where I walk from root to each leaf, kind of leftmost to rightmost. And then instead of recording the edges, now I'm going to record the vertices. And so, for example, for this tree, what I do is I start at 3, and then I would go to 2, and then 1, and then 2, and then 3. And what you'll see is this Gaussian sequence exactly records that walk. Over here, I go 3, 2, 3, 1, 3 to get this one. And then finally, I go 3, 1, 3, 2, 3. Okay. And so, kind of, this is a little figure, at least showing you the general proof of this bijection, at least in the case when d equals 3. Okay. And so, oh good, it looks like I'm pretty much right at time. And so that's pretty much all I'm going to share from this paper. And so just some kind of key takeaways. So we're able to give bounds on the number of connected components for these Gaussian Voronoi diagrams. And in particular, maybe more applicable, we're able to give lower bounds. Namely, we're able to show that these kind of give bounds on how many of these Voronoi cells can be empty, which has pretty significant algorithmic implications. We're then able to classify which sequences are Gaussian sequences and count the number of such sequences. So essentially, we're able to associate a combinatorial type to at least these Gaussian Voronoi diagrams in one dimension, and then count the number of combinatorial types. I'll say there's going to be more details and then additional results regarding these decision boundaries and discriminants and things like this in a hopefully shortly published forthcoming paper. So with that, I can stop and take any questions.
Let's thank the speaker by clicking buttons, and then we'll stop the recording here.